Okay, so chapter 12 is mostly review, going back to probably chapter 3 of your book, which is linear regression. Okay, big AP topic is to make sure that you can look at one of these computer printouts and get the equation of the least squares line, right? So up here in this is your scatter plot, and then another piece of this that's going to be review is this other plot. That's your residual plot, right? So what you want to remember about these residuals, I don't know if I can draw on here or not, let's see. But like if I have, let's say I have the line of best fit, different color here. Just going to make one up. This is my line of best fit running through here. The residuals are the errors, right? So the line of best fit makes a prediction that's too low for this point. Makes a prediction that's too high for this point, right? Those are my residuals. So the residuals are the errors. They can be positive and negative. If you add them all up, they're always going to add up to 0. So when I want the equation of the least squares line, though, I want to lock in on right here, these two numbers, okay? The coefficient of the constant term, that's your y-intercept. So the y-intercept for this least squares equation would be 70.44. The slope would be 274.78. So it's going to look something like we're trying to predict velocity, right? So it's going to be velocity equals 70.44 plus 274.78 times thickness, okay? You have your r squared number here, 49.3%. So what does that mean, right? It means 49.3% of the change in velocity is explained by thickness, okay? So if we had no other way of explaining this, we didn't look at a scatter plot, we would just measure standard deviation as the measure of variation. But as we move along here on the x-axis, we can see a pattern is happening with velocity. It seems to be somewhat increasing, right? So we're explaining velocity using thickness. We're using the least squares regression line model. How well do we do that? Well, 49.3% of that change is explained by it. It's not a prediction percentage of accuracy. You don't want to say the line is 49.3% accurate in making predictions, because I don't know if I can draw one or not, but like what if I had a least squares line that didn't hit any points? So its percent accuracy is actually 0, right? But it's still the line of best fit. So it's not the percentage of predictions that are correct. It's just percentage of change in velocity that's explained by thickness. So the closer these do live to that line of best fit, the better the model is, okay? The stuff that is new now is that you've got a t statistic over here and a p-value, okay? Unfortunately, they don't give us the t statistic and the p-value that we actually need. We're never really doing anything with the y-intercept. Testing the y-intercept doesn't tell us anything. Testing the slope tells me if there's a significant relationship between these two, right? Think about the slope of a line that's 0. If a line has a slope of 0, right? If I got my line of best fit for a bunch of points, if the line of best fit is 0, what does that mean? It means that, or the slope of the line of best fit is 0, that's a horizontal line. It means there's no relationship between x and y, okay? If the slope of the line is then significantly different from 0, so that's what we want to do. We want to see, is this number 274.78 significantly different than 0, so that we would conclude that there is a relationship between those two. So when you run a hypothesis test on something like this, your null hypothesis is going to be that beta, the true population slope of the least squares line, usually it's going to be 0. The alternate then becomes usually, not always, beta not equal to 0, right? If I reject the null hypothesis, which I don't have a p-value here to see it, okay? But we can very easily get the p-value, okay? That for a linear regression t-test, the t-test statistic is the easiest one you're ever going to do. You just take the slope, your sample slope, 274.78. You just take that sample slope and divide by the standard error number that's right next to it, 88.18. That's how you'll get t. And then how do we use that? Well, we look it up with a certain number of degrees freedom. Your degrees freedom here is a little bit different, okay? Before with means we used n-1. Just think 2 variables, so do n-2, okay? So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So n is 12, that means I would have 10 degrees freedom here. Right? So if I wanted the p-value, so I get the t statistic, I showed you how to get t. If I wanted the p-value for a two-tailed test, remember what we do. You can use TCDF. TCDF, right? It's like normal CDF, but you find the area in this tail, because you're going to get a positive test statistic. And if you just find the area in the one tail, then you can double it, and that'll be your p-value if it's a two-tailed test. Okay? So that's basically what the review question is asking you down here. It's basically saying, let's erase this. Okay, so describe what the scatter plot tells you about the relationship between cylinder wall thickness and gate velocity. So I always tell my students to remember the acronym SOFA, S-O-A, or S-O-F-A, right? Strength, so I look at this and say, is it really strong, is it moderate, or is it weak? I'd say it's probably moderate, right? O is for outliers. Do I see any outliers in this scatter plot? Not really. Not anything that doesn't really fit the general overall pattern. Form, you're either going to say it's linear or it's nonlinear. So if I don't see that it's curving or bending, then linear should be good. If you look down here, you can see, look at this bend, sort of a bend in the scatter plot. So that I would say the form is kind of nonlinear. Definitely a nonlinear form down here. All right, but up here in this one, I don't have any reason to believe this isn't a linear model. So I would say it's moderate, moderate in strength, roughly linear, no outliers, and the association, is it positive or negative? If I drew the line of best fit, would it have a positive slope or a negative slope? Or here's my slope of the line of best fit, so that tells me right away it's positive, right? Down here you have the residual plot. It's the plot of the errors, okay? This positive residual up here means that the prediction by the least squares line was too low, okay? That means at that point lived up above the least squares line, it was too low. The other thing you want to make sure you remember about residuals, big idea, and it should be in the notes that I give you, is that the residual for any point, this is super important. It's not cooperating with me. So a residual equals, it's the actual y value minus the predicted. So there you go. The residual equals the actual minus the predicted. Clear that. Clear that. Let's get this back to a normal size now. Okay, equation of the least squares line. Again, that would be predicted predicted velocity. And that's the thing, when you write that equation, make sure you put the hat over the velocity, like y hat or velocity hat. So if you're writing velocity, you put a hat over top of it, right? Velocity, predicted velocity equals. Make sure you differentiate between those two. Is the model appropriate? Let's get rid of this. Right, so part C, you're going to use the residual. Does it overpredict or underpredict, right? So in that case, one of the cylinders in the sample had a wall thickness of 0.4 inches, right? So that's X. You're going to take that, plug it into your least squares equation up here, okay? You're going to take that value, plug it in there. Oh, I didn't want to do that. Go back. And then figure out what the predicted velocity would be for that. Its actual velocity was 104.8. So you're going to take 104.8 minus the predicted value, right? So it's 104.8 minus whatever you get when you plug this 0.4 inches into that equation up there, right? Up. There. Back down. Okay. Interpret each in context, right? The slope. So what does the slope of the least squares line tell me in context here? On average, for each increase in thickness, right, of an inch, for each increase in an inch of thickness, and watch this with slope, it's the predicted velocity is increasing by 274.78. You don't want to just say like a general slope definition like as thickness increases by an inch, velocity increases by 274.78. You want to say, it's subtle, but you want to say predicted velocity increases by 274.78. Okay, it's the slope of the least squares line, so it's not like the actual velocity changes by that much every time. This little guy S here, what's that referring to? It's referring to this number up here, 56.36. Two ways you could describe it. It's the standard deviation of the residuals. It's referring to, on average, how big the errors are. Or I think the best way to explain it here would be to call it a typical prediction error. So, if I use these numbers here, these equation least squares line, to predict velocity, then on average, my predicted velocity is going to differ from my actual velocity by about 56.3641. Okay, a lot of that should be review. R squared, we already talked about that. And standard error of the slope, that's this guy here. This is marrying the new concept of the sampling distribution and standard error with the old concept, right? So we took one sample of 12, we made a least squares regression line here, and that's a sample slope. So this slope, 274.78, we can expect this 274.78, or any sample slope, to differ from beta, right, the true population slope. Okay, we get beta, we use little b to estimate it. So this is like p hat, and this is p. This is like x bar, and this is like mu. So we'd expect this b here, which is what we estimated here, to differ from beta by about 88.18. Okay, that's the standard error of the slope. It's a standard deviation of the sampling distribution, kind of the same definition that you've had a standard error for probably a bunch of chapters.